Electrons flowing exclusively along the absolute edge of a material, while the interior remains completely frozen to electrical current, define a topological insulator. This unique boundary conduction is not caused by chemical contamination, but by the mathematical topology of the bulk electronic wave functions inside the crystal lattice structure. Traditional insulators block electrical current because their valence and conduction energy bands are separated by a clean, impassable energy gap containing no electronic states. In a topological insulator, strong relativistic spin-orbit coupling inverts the typical energy ordering of these bands, forcing them to cross at the boundaries. This band inversion creates gapless surface states where electrons move freely, completely bypassing the insulating bulk interior of the main crystal lattice structure.
Geometric topology classifies physical shapes by continuous deformations, like stretching or twisting, without tearing, where a donut and a coffee cup share identical properties. In quantum mechanics, the electronic wave functions plotted over the periodic Brillouin zone form an abstract parameter space directly analogous to these geometric surfaces. The topological invariant, known as the Chern number, mathematically counts how many times the quantum wave function wraps around this geometric momentum space grid. When a material with a non-zero invariant meets a trivial vacuum, the invariant cannot change continuously, forcing the interface to host metallic states. This phenomenon originates from the quantum Hall effect, where intense external magnetic fields force bulk electrons to move in tiny circular cyclotron orbits.
At the physical edge of the material, these circular orbits cannot complete, forcing the electrons to bounce forward in one single direction. These one-way edge channels are completely immune to backscattering because there are no available backward-moving states for electrons to turn around. Topological insulators achieve this exact robustness without any external magnetic field, relying instead on internal, intrinsic, relativistic spin-orbit interactions of heavy elements. This variation is the quantum spin Hall effect, where forward-moving electrons possess spin-up orientations and backward-moving electrons possess spin-down orientations. This rigid correlation between the linear momentum of an electron and its intrinsic magnetic spin orientation is formally called spin-momentum locking. If an electron encounters a normal, non-magnetic impurity, it cannot bounce backward, because doing so would violate the conservation of its spin state. Time reversal symmetry protects these specific states, ensuring that the forward and backward spin channels cancel out any potential destructive backscattering interference. The binary classification of these materials utilizes the modulo 2 topological invariant, which rigorously separates ordinary insulators from true topological insulators. Graphing the electron energy against its momentum reveals a linear dispersion relation, creating a distinct visual shape known as a Dirac cone. The intersection vertex of this cone is the Dirac point, where electrons behave exactly like massless relativistic fermions moving at a constant speed. Bismuth selenide and antimony telluride are classic examples of three-dimensional topological insulators. Their bulk crystal structure functions as an excellent insulator, while their outer physical boundaries naturally host highly conductive, two-dimensional metallic surface states that are robust against external perturbations. Angle-resolved photoemission spectroscopy directly verifies these unique band structures by shining high-energy ultraviolet photons onto the crystal surface. This process ejects electrons, allowing detectors to measure both their precise kinetic energy and emission momentum, visually mapping out the expected linear Dirac cones. Unlike the one-dimensional edge channels found in two-dimensional systems, the surface states of a three-dimensional topological insulator allow electrons to move anywhere across the outer faces. However, the requirement of spin-momentum locking still prevents these electrons from shifting directly backward. Slicing or fracturing a topological insulator crystal does not destroy its unique electrical properties. Because the topological invariant is a fundamental characteristic of the entire bulk material, Any newly exposed interior boundary immediately reorganizes its quantum wave functions to form fresh, robustly conducting surface states. The metallic surface conductivity is completely unavoidable unless you deliberately break time reversal symmetry. This destruction can be achieved by introducing magnetic dopants into the crystal lattice, or by applying an intense external magnetic field, which disrupts the delicate balance between opposite spin states. Breaking time reversal symmetry forces a fundamental change in the electronic band structure, opening a clear energy gap right at the Dirac point. This gap removes the massless nature of the surface electrons, converting the outer perimeter from a robust conductor back into an ordinary insulator. Placing a topological insulator in direct atomic contact with a conventional superconductor triggers an extraordinary phenomenon known as the superconducting proximity effect. Cooper pairs of electrons leak across the interface, inducing an exotic state of matter called a topological superconductor within the surface states. This engineered topological superconducting interface hosts highly sought-after quasiparticles called Majorana bound states. Unlike conventional electrons, these emergent zero-energy excitations act as their own antiparticles, meaning that a Majorana particle is completely identical to its corresponding antiparticle within the host system. Majorana fermions do not follow standard bosonic or fermionic statistics, obeying non-abelian braiding statistics instead. When you physically swap the positions of two Majorana-bound states, the operation performs a non-trivial unitary transformation on the global wave functions, fundamentally altering the quantum state. This unique braiding behavior forms the physical foundation for fault-tolerant topological quantum computing. Instead of encoding qubits in vulnerable local states like individual electron spins, information is stored globally in the non-local configuration of multiple separated Majorana bound states across the circuit. Because the quantum information is encoded non-locally, it becomes entirely immune to local environmental disturbances. Normal sources of quantum decoherence, such as stray magnetic fields, structural crystal defects, or thermal fluctuations, cannot corrupt the data unless they are large enough to affect the entire system simultaneously. Beyond quantum computation, these materials offer massive potential for next-generation spintronics. Spin momentum locking ensures that passing an ordinary electrical current through the surface state naturally generates a highly polarized spin current, allowing engineers to manipulate magnetic data storage elements with minimal energy dissipation. This efficient spin generation allows for the creation of advanced spin-orbit torque magnetoresistive random access memory devices. By passing a current through the topological insulator layer, the resulting spin accumulation exerts a powerful torque on an adjacent ferromagnetic layer, switching its magnetic orientation ultra-rapidly. Theoretical and experimental discoveries have expanded this domain to include higher-order topological insulators. While a standard three-dimensional insulator hosts conducting two-dimensional faces, a second-order topological insulator remains insulating on its faces, confining its conductive channels to one-dimensional hinges or corners. The core mathematical principles of electronic topological insulators have been successfully translated into optics and acoustics. By arranging macroscopic dielectric pillars or acoustic resonators in specific geometric patterns, researchers can create photonic and acoustic topological insulators that steer light and sound waves perfectly around sharp corners. Despite their immense theoretical promise, real-world implementation faces significant engineering obstacles. Ideal crystals should have a completely insulating interior, but natural crystal defects, such as selenium vacancies in bismuth selenide, often create unwanted bulk carrier density that masks the pure surface conduction effects. To combat this unintended bulk conductivity, material scientists employ advanced compensation doping strategies. By deliberately introducing precise amounts of counterdopants, like calcium or antimony, into the crystal melt, they can successfully neutralize the native defects and force the Fermi level back into the bulk energy gap. Another powerful approach is fabricating ultra-thin films using molecular beam epitaxy under ultra-high vacuum conditions. This method allows researchers to synthesize highly crystalline layers with atomically flat interfaces, significantly maximizing the surface-to-volume ratio and making the topological surface states dominate the overall transport measurements. Discovering or engineering new material systems that exhibit these robust topological phenomena at room temperature is a primary objective for current solid-state research. Achieving this milestone would allow topological components to integrate directly into consumer electronics without requiring expensive and bulky cryogenic cooling systems. By seamlessly merging topological stability, dissipationless edge transport, and intrinsic spin polarization, topological insulators provide a clear evolutionary path beyond the physical limits of traditional silicon semiconductors, paving the way for ultra-energy-efficient microprocessors and truly scalable quantum processing units.